Good morning everyone. So today we are going to discuss the last section related to power series solution. So in this we are going to see a very specific kind of differential equation and its solution would be in a very specific form. So this specific equation would be known as hypergeometric equation and the solution would be hypergeometric series solution. So a differential equation of the form x1 minus xy double dash plus c minus a plus b plus 1xy dash minus aby is equal to 0, where a, b, c are constant, is known as the hypergeometric equation. So you can see here that x is equal to 0 and x is equal to 1, both are regular singular points. So for this equation we will find the Frobenius series solution for both x is equal to 0 and x is equal to 1. We already know how to find about x equal to 0. So in today's lecture we also see that how do we find the Frobenius series solution about x is equal to 1. But we start with x is equal to 0. So for x is equal to 0, the solution looks like summation a n x raised to the power n plus r. If you substitute y into the given equation 1 and rearrange some terms, then it would look like this one. I'm not going into all these details. Please do computation by yourself. Now first step is to find the initial equation. So equating the coefficient of x raised to the power r minus 1. So only the first term gives me this one. Here I can add an. So a naught r, then this is c plus r minus 1 is equal to 0. That gives you r is equal to 0 and 1 minus c. At this stage c is unknown, so I am not going into the detail for finding for r is equal to 1 minus c, but initially we will start with r is equal to 0. Now to have the recurrence relation, I equate the coefficient of x raised to the power n plus r minus 1 to 0. There are only two terms, so that gives me a recurrence relation for an which looks like this one, and r is equal to 0. So if you see this recurrence relation is very interesting. An minus 1 and n is greater than equal to 0. So from this recurrence relation, a1 is a dot b by 1 dot c, then a2 is a plus 1 b plus 1, then 1 dot 2 c plus 1. So you can see that it is very easy to find the general term here. So the general term would be a plus 1, a plus 2, and it goes to a plus n minus 1. Similarly for b and c, and the denominator we would have n factorial. So it means I can write y of x as this and identify the general term. But if I substitute a naught is equal to 1, then this series or the solution which I got for r is equal to 0 about x is equal to 0 is known as the hypergeometric series, and it is denoted as f of a comma b comma c comma x. So it's very easy to remember this series. It is 1 plus summation n starting from 1 to infinity and going to a plus 1 going till a plus n minus 1. Similarly b plus 1, b plus n minus 1. Same is for the c, and n factorial. So it's very easy to remember. Yes, and we have to remember it. So this is the hypergeometric series solution for r is equal to 0, and the standard notation is f of a comma b comma c comma x, provided c is not equal to 0 and c is not a negative integer. So you can see that if you put c is equal to 0 or c is equal to any negative integer, then the series is not defined. Now quick remarks. First easy remark is f of a comma b comma c comma x is same as f of b comma a. So you can interchange b and a because you can see here that both are in the numerator. So you can easily interchange them. The next remark is if you put a is equal to 1 and b is equal to c, so b and c would cancel out and it will become, for example, when you find the coefficient of x square, it becomes a is 1, so 1 and 1 plus 1, so 1 dot 2, and in the denominator it is 2 factorial, so it will always keep cancelling, and that's why it will simply becomes a geometric series of the form 1 plus x square and so on. So this is just to see that why we call it hypergeometric series, because it is the generalization of this geometric series. The last remark is about the convergence of hypergeometric series. So can you see that where it is convergent? So for convergence, recall that we have discussed the ratio test, which says that the values of x for which limit n tends to infinity, a n plus 1 x n plus 1 divided by a n x n should be less than 1. So let's see what is a n plus 1 by a n. So if you see the recurrence relation here, then from this recurrence relation it is a n and a n minus 1. It means my a n plus 1 is a plus n, b plus n, then c plus n, and n plus 1 and a n. If I take a n on that side, so this would be my a n plus 1 by a n. Yes. So using this, I will get ratio test as this xn plus 1 by xn, so it only remains mod x. This is a n plus 1, b n plus 1, n plus 1, c n. So mod x I can take out, and if I compute the value of limit n tends to infinity, so limit n tends to infinity, and this becomes, if I divide it by n square numerator and denominator, it becomes a by n plus 1, b by n plus 1, 1 plus 1 by n, and c by n plus 1. So now when n tends to infinity, a by infinity it's 0, b by infinity is 0, c by infinity 0, and 1 by infinity is 0, so it only remains 1. That's why I have mod x is less than 1, which means that the hypergeometric series f of a comma b comma c comma x is analytic for mod x less than 1. Yes. So these are the three important remarks. Now the next thing is, we have computed the solution for x is equal to 0. Now I need for x is equal to for r is equal to 0, and now I need for r is equal to 1 minus c. Now for r is equal to 1 minus c, the solution would look like y of x, then x raised to the power r, so x raised to power 1 minus c, and then there is a power series, and we need to compute the value of these coefficients. But this gives us the solution as an Frobenius series solution. What I am looking for is the hypergeometric series solution. So we need to find the hypergeometric series solution for r is equal to 1 minus c. Now the hypergeometric series solution, for finding the hypergeometric series solution, we will change the dependent variable. So let's say the solution would look like y of x is equal to x raised to the power 1 minus c z of x. Now from this y of x I can compute y dash, y double dash, and put it back into the equation 1. That gives me an equation in z. Yes, this exercise you need to do it by yourself. If you do it and rearrange the term, then you will see that you will get the following equation: x 1 minus x z double dash plus 2 minus c minus a minus c plus 1 plus b minus c plus 1 plus 1, and so on. Now if you compare it with the hypergeometric equation, then you will realize that in the hypergeometric equation this was same, this was y, so it is z, not a problem. Instead of 2 minus c I have c, instead of a minus c plus 1 I have a, b minus c plus 1 I have b, and so on. It means that if I compare it with the hypergeometric equation, which is this one, and I know that what is the solution of the hypergeometric equation about x is equal to 0 for r is equal to 0. So for the same hypergeometric equation in z, since it is a hypergeometric equation, so if I replace in the solution f of a comma b comma c comma x, so I replace a by a minus c plus 1, b by b minus c plus 1, and c by 2 minus c. Then I will get z is equal to f of a minus c plus 1, b minus c plus 1, 2 minus c, and x, because it is a hypergeometric equation and a, b, c are constants. So if you compare it, just the c, instead of c I have wrote 2 minus c, instead of a I wrote a minus c plus 1, and for b I wrote b minus c plus 1, and that's why I can write down this solution. It means that the general solution, and I can say about x is equal to 0 for equation 1 is y of x c1 f of a comma b comma c comma x plus c2 x raised to the power 1 minus c f of a minus c plus 1 b minus c plus 1 2 minus c comma x. Now tell me that, do you see any restriction on c? Yes, please figure it out. So if you figure it out, then from here we have seen that c is not equal to 0, c is not an negative integer. From here, if you see in the denominator, you will have 2 minus c, because c is c plus 1, so 2 minus c, then 3 minus c, and so on. It means c cannot be equal to 2, 3, 4, and so on. So c cannot be equal to 2, 3, 4, c cannot be negative integer, c cannot be 0. But I wrote provided c is not an integer. So why only term missing is c is equal to 1. Can c be equal to 1? If c is equal to 1, then I will get equal roots. So for c is equal to 1, equal roots. In case of the equal roots, there exists only one Frobenius solution. So if I want two Frobenius solution, then I should not consider c equal to 1. And because of this, I will get c is not an integer. Yes. Now next is to find the hypergeometric series solution about x equal to 1. Till now we have only seen about x equal to 0. Now for x is equal to 1, the idea is simple. I have to change the independent variable. Why? Because I know the solution about x equal to 0 for the hypergeometric series solution. If I change a variable, for example, t is equal to 1 minus x, and if I transform the hypergeometric series solution, I know its solution about t is equal to 0. Now t is equal to 0 is same as x is equal to 1. So let's substitute t is equal to 1 minus x into the given hypergeometric equation and see what we are getting. Again, you need to do this exercise and it will transform into this form. Just for clarification, you can compute dy by dx, which comes out to be minus dy by dt, and d2y by dx square comes out to be d2y by dt square. Yes, and this is how it get transformed into an hypergeometric equation. Hypergeometric equation in t, where this is the only term which get replaced. So c got replaced by a plus b minus c plus 1. The rest it is as it is. It means that for this hypergeometric equation which we obtained, I can write down the solution about t is equal to 0. And then in that solution, if I replace t as equal to 1 minus x, then that gives me the solution about x is equal to 1. So you can see that here I replace c by a plus b minus c plus 1. Here I replace x by 1 minus x because I got the solution in t. And this is the solution about x is equal to 1 for the given hypergeometric equation. So in today's class, we have seen how to find the hypergeometric series solution about x equal to 0 and x is equal to 1. In the next class, we will compute the hypergeometric series solution for the different values of x. For example, x is equal to 3, 4, and so on. So thank you very much.